Picture this, somewhere out in the vast darkness of space, invisible to our eyes but screaming with unimaginable energy, beams of light so powerful they could pierce through planets are constantly flashing across the cosmos. These are gamma rays, the universe's most extreme form of light, carrying secrets we're only beginning to unravel. And here's what will blow your mind. Even when we look at seemingly empty patches of space, we find them bathed in a mysterious glow of gamma radiation that no one can fully explain. This is the cosmic gamma ray background, an invisible tapestry of high-energy puzzles that defies everything we think we know about space. Today, we're diving into 25 of its strangest mysteries, from ghostly flashes with no known source to bizarre structures that shouldn't exist. Some of these cosmic riddles might be signs of dark matter. Others could rewrite the laws of physics as we know them, and by the end of this journey, you'll see the night sky in a whole new light, knowing it's crackling with invisible energy and unanswered questions that scientists are racing to solve. So let's begin. Now let's peel back the first layer of this cosmic enigma. Imagine you're holding a flashlight in a pitch-black room, but instead of a single beam, the entire room glows faintly from every direction. That's the puzzle of diffuse gamma rays. They're everywhere, filling the space between galaxies, yet no one can pinpoint exactly where they're coming from. Some scientists think these rays might be the fingerprints of dark matter, the invisible stuff that makes up most of the universe's mass. If dark matter particles collide and annihilate, they could spit out gamma rays, lighting up the cosmos in this eerie glow. Others argue it's something more ordinary, countless faint sources like pulsars or black holes, too dim to spot individually but adding up to a cosmic haze. But here's the twist, neither explanation fits perfectly. The gamma rays don't match the patterns we'd expect from dark matter, and there simply aren't enough known astrophysical objects to account for all of them. It's like trying to solve a jigsaw puzzle where half the pieces are missing, and the ones we have don't quite fit. This mystery isn't just about gamma rays. It's a tug of war between the known and the unknown, forcing physicists to question whether they're missing something fundamental about how the universe works at its most extreme energies. And until we crack it, the cosmos keeps whispering its secrets in a language of light we're still learning to decode. Now, let's shift our gaze closer to home, right to the heart of our own galaxy. Picture two colossal bubbles, each towering tens of thousands of light years above and below the Milky Way center, glowing with gamma rays. These are the Fermi Bubbles, and they're one of the most baffling structures in our cosmic backyard. Discovered just over a decade ago, these giant lobes weren't predicted by any theory. They're like finding a pair of invisible mountains in your backyard that no one knew were there. What makes them even stranger is their gamma-ray glow. These bubbles shouldn't be emitting such high-energy light unless something incredibly violent happened in our galaxy's core. One leading theory points to Sagittarius, a star, the supermassive black hole at the Milky Way center. Some scientists think it might have erupted in a massive outburst millions of years ago, spewing jets of energy that inflated these bubbles like cosmic balloons. Others argue it could be the aftermath of a frenzy of star formation, where countless exploding stars pumped energy into the galaxy's heart. But here's where things get murky. The gamma-ray signal from the bubbles doesn't perfectly match either scenario. If it were a black hole eruption, we'd expect to see other clues like shock waves or X-rays, but those are missing. And if it were star formation, the bubbles should look different, more patchy, less symmetrical. It's like having two suspects in a cosmic whodunit, but neither one leaves a perfect fingerprint. This mystery isn't just about the bubbles themselves. It's a window into the Milky Way's violent past, where we witness to a cataclysmic black hole tantrum. Or did something else entirely shape these eerie structures? Until we know for sure, the Fermi Bubbles remain a glowing reminder that even our own galaxy still has secrets to spill. Now, let's turn our attention to another cosmic enigma, one that spins at the heart of some of the universe's most precise clocks. Pulsars are often called nature's lighthouses, beaming radiation in predictable pulses as they rotate with mind-boggling regularity. But some of these cosmic timekeepers are breaking the rules, emitting gamma rays in ways that leave scientists scratching their heads. Take their timing, for example. Pulsars are famous for their rhythmic flashes, some ticking with the precision of atomic clocks. Yet a handful of them produce gamma-ray bursts that don't align with their expected pulse patterns. It's like a metronome suddenly skipping a beat or adding an extra tick out of nowhere. These irregularities suggest there's something about the pulsar's magnetic field or surrounding environment that we don't fully understand, something twisting the rules of physics in ways our models can't yet explain. Then there's the puzzle of their spectra, the unique fingerprint of light they emit. Normally, pulsars shine brightest in radio waves or X-rays, with gamma rays being a secondary feature. But some gamma-ray pulsars flip this script, blasting out high-energy light far more intensely than predicted. Even stranger, a few of them seem to switch between different emission modes, as if they have a hidden dial adjusting their output. Scientists have proposed theories, from twisted magnetic fields to exotic particle interactions near the pulsar's surface, but no single explanation fits all the oddities. And let's not forget where these misfit pulsars are found. Some lurk in regions where they shouldn't exist, like dense star clusters where gravitational chaos should disrupt their delicate beams. Others sit oddly isolated, with no clear source for the energetic particles fueling their gamma-ray glow. It's as if the universe hid these pulsars in plain sight, daring us to figure out why they don't play by the rules. What makes these outliers so fascinating isn't just their defiance of expectations, it's what they might teach us. Every anomaly is a clue, hinting at gaps in our understanding of how pulsars work, how particles accelerate to such extreme energies, or even how matter behaves in the most intense gravitational fields imaginable. Until we crack their code, these gamma-ray pulsars will keep spinning mysteries into the cosmos, one unpredictable pulse at a time. Now, shifting our gaze to the far reaches of the universe, we encounter another head-scratcher, blazars that don't quite add up. These cosmic powerhouses, active galactic nuclei with jets pointed straight at us, are some of the brightest gamma-ray sources in the sky. They should, in theory, be major contributors to the gamma-ray background. But here's the twist: when scientists tally up all the known blazars, their combined glow falls short. There's a glaring gap in the cosmic ledger, leaving a significant portion of the gamma-ray background unaccounted for. So where's the missing light coming from? One possibility is that we're simply not seeing all the blazars out there. Some might be too faint or too distant for our telescopes to spot, lurking just beyond the edge of detection. Others could be hiding in plain sight, their jets angled just slightly away from us, dimming their gamma-ray signal. It's like trying to count fireflies on a foggy night. You know there are more out there, but the haze makes it impossible to catch every flicker. But there's a more tantalizing alternative. What if the missing gamma rays aren't from blazars at all? Some theories suggest entirely new classes of objects could be at play, ones we haven't even discovered yet. Imagine stumbling upon a cosmic phenomenon that doesn't fit any existing category, a celestial wild card rewriting the rules. Others speculate that the gap might hint at exotic physics, like particles or interactions beyond our current understanding. Could dark matter be sneaking into the equation, or are we seeing echoes of processes from the early universe? The mystery deepens when you consider how blazars behave over time. These objects aren't steady beacons, they flare and fade unpredictably. Could their flickering nature mean we've underestimated their total contribution? Or does it point to something even stranger, like intermittent sources that switch on only under rare conditions? Each unanswered question pulls us deeper into the puzzle, reminding us that the universe always keeps a few cards close to its chest. What makes this enigma so compelling is its ripple effect. If hidden blazars are the answer, it means our maps of the cosmos are still incomplete. But if new physics is involved, it could open doors to discoveries that reshape our understanding of reality itself. Either way, the missing blazar contribution isn't just a gap in data. It's a beacon guiding us toward the next great cosmic revelation. And as we'll soon see, the gamma-ray background has even more surprises in store. Now, let's turn our attention to one of the most puzzling leftovers in the gamma-ray sky, the faint afterglow of gamma-ray bursts. These cosmic explosions are some of the most violent events in the universe, capable of outshining entire galaxies for a brief moment. But here's the strange part. Long after the initial flash fades, a whisper of gamma rays lingers, defying expectations. Scientists expected these bursts to vanish quickly, like a firework dissolving into the night. Instead, they've detected a stubborn afterglow that persists, sometimes for years. It's as if the universe forgot to turn off the lights. One explanation is that we're seeing echoes, gamma rays bouncing off clouds of dust or gas, creating a delayed signal. Imagine shouting into a canyon and hearing your voice return moments later, but stretched and distorted. But there's a more intriguing possibility. What if this afterglow isn't just an echo but a sign of something entirely new? Some theories suggest exotic physics, like quantum foam or hidden dimensions, could be altering how gamma rays travel through space. Others wonder if the bursts leave behind unstable particles that decay slowly, releasing gamma rays long after the main event. It's like finding embers still glowing in a campfire that burned out years ago. Something is keeping the energy alive, and we don't quite know what. The mystery deepens when we consider how these afterglows vary. Some fade predictably, while others flicker unpredictably, as if something is interfering with them. Could there be invisible structures in space, cosmic filaments, or dark matter halos scattering the gamma rays in ways we don't yet understand? Or are we seeing the fingerprints of a process that challenges our models of particle physics? What makes this enigma so fascinating is its potential to rewrite the rules. If the afterglow is just an echo, it tells us about the environment around these bursts, the cosmic debris left in their wake. But if it's something stranger, it could hint at physics beyond our textbooks. Either way, these faint signals are like postcards from the edge of the unknown, reminding us that even the universe's most fleeting moments can leave a lasting mark. And as we'll see next, the gamma-ray background has even more secrets waiting to be uncovered. Now, let's journey to the heart of our own galaxy, where another gamma-ray mystery is waiting to be unraveled. Deep in the Milky Way's core, astronomers have detected an unexpected surplus of gamma rays, a glow that shouldn't be there. This so-called galactic center excess has sparked a fierce debate, with two leading explanations vying for dominance: dark matter or pulsars. But here's the twist: neither one quite fits the puzzle. First, let's talk about the dark matter angle. Some scientists believe this excess could be the smoking gun for dark matter particles annihilating each other, releasing gamma rays in the process. It's an exciting idea because dark matter is invisible, leaving almost no trace except perhaps this eerie glow. If true, it would be one of the biggest discoveries in modern physics. But there's a problem. The gamma-ray signal doesn't perfectly match what dark matter models predict. It's like hearing a song that's almost familiar, but the notes are just slightly off. On the other hand, pulsars, fast-spinning neutron stars, could also be the culprits. These cosmic lighthouses emit gamma rays, and the Milky Way's center is packed with them. Maybe we're just seeing the combined glow of thousands of undiscovered pulsars. But again, the data doesn't fully cooperate. The gamma-ray distribution is smoother than what you'd expect from a crowd of pulsars, which should create a more clumpy pattern. It's as if someone took a jar of glitter and shook it until the specks blurred into a uniform haze. So where does that leave us? Some researchers are now exploring hybrid theories. Perhaps it's a mix of both dark matter and pulsars, or maybe something entirely different, like cosmic rays slamming into gas clouds in unexpected ways. The galactic center excess is a reminder that even our own backyard in the cosmos can hold surprises that defy easy explanations. And as we'll soon see, the gamma-ray sky has even more twists in store for us. But here's something even more puzzling: gamma rays don't spread evenly across the sky like a smooth blanket of light. Instead, they gather in strange clumps and leave behind empty patches, almost like a cosmic game of connect the dots. This unevenness, called anisotropies, tells us there's more going on behind the scenes than we ever imagined. At first glance, you might think these clumps come from known sources like blazars or pulsars. But when scientists mapped them out, the pattern didn't match. Some gamma-ray hotspots have no obvious origin, while other areas are suspiciously quiet. It's as if the universe left us a map with half the landmarks missing. One leading theory suggests these irregularities could trace the hidden scaffolding of the cosmos' vast filaments of dark matter weaving through space, pulling matter together into invisible structures. If gamma rays are lighting up these dark highways, it could revolutionize how we understand the universe's large-scale architecture. But there's another twist. Some anisotropies might be echoes of ancient cosmic violence, like supermassive black holes erupting billions of years ago, their shockwaves still rippling through space. Or perhaps they're hints of entirely new phenomena, something we haven't even dreamed up yet. What makes this mystery so thrilling is that every irregularity is a clue. Whether it's dark matter's fingerprint or a relic of long-forgotten explosions, the gamma-ray sky's uneven glow is a reminder that the universe loves to defy our expectations. And as we'll see next, some of its secrets are hiding in plain sight where nothing seems to be there at all. Now, let's turn our attention to one of the most baffling chapters in the gamma-ray saga: the unidentified sources. Imagine pointing a telescope at the sky and seeing bright flashes of gamma rays, only to look closer and find nothing. No stars, no galaxies, no black holes, just empty space where these high-energy signals seem to originate. Hundreds of these ghostly gamma-ray detections litter the cosmos, defying every attempt to match them with known objects in other wavelengths. It's like hearing a voice in a crowded room but turning around to see no one there. Some could be exotic objects we've never seen before, cosmic oddities that don't emit light the way typical stars or galaxies do. Others might be glitches in our instruments, echoes of particles interacting in ways we don't yet understand. One tantalizing possibility is that these sources are hiding in plain sight, camouflaged by distance or dimness. For example, a faint pulsar spinning just beyond our detection threshold could be pumping out gamma rays without revealing itself in visible light. Or perhaps they're remnants of rare stellar collisions, so brief and violent that they leave no trace except this fleeting energy. Then there's the wild card: what if these unidentified signals are the work of something entirely new? Theorists have floated ideas like decaying dark matter particles or even microscopic black holes evaporating in bursts of radiation. Each unexplained detection is a breadcrumb leading us toward discoveries that could rewrite the textbooks. What makes this mystery so gripping is its sheer unpredictability. Every time we think we've catalogued the universe's energy sources, gamma rays remind us how much we still don't know. And as we'll see next, some of these enigmas aren't just isolated dots on a map, they're woven into the very fabric of galaxies themselves. But here's something even more puzzling: gamma rays coming from places we least expect. Take galaxy clusters, for instance. These colossal gatherings of hundreds or even thousands of galaxies bound together by gravity should, in theory, be relatively quiet when it comes to gamma rays. Yet they're not. Galaxy clusters are like cosmic metropolises bustling with hot gas, magnetic fields, and swarms of high-energy particles. When cosmic rays, those speedy protons and atomic nuclei zipping through space, collide with the cluster's gas, they can produce gamma rays as a byproduct. But here's the catch: the amount of gamma radiation we detect often exceeds what our models predict. It's as if these clusters are hiding extra factories churning out gamma rays, and scientists are scrambling to figure out where they're coming from. One leading idea points to dark matter. If dark matter particles, those invisible, mysterious components of the universe, annihilate or decay within these clusters, they could be the unseen source of this excess gamma radiation. Imagine entire galaxies wrapped in halos of dark matter, silently producing bursts of energy we can't explain any other way. Then there's the possibility of extreme cosmic accelerators within these clusters. Turbulent magnetic fields or shockwaves from galaxy collisions might be revving up particles to energies we've never witnessed before, creating gamma rays in ways we haven't accounted for. What makes this mystery so compelling is its scale. Galaxy clusters are among the largest structures in the universe, and if they're producing gamma rays beyond our expectations, it suggests there's a whole layer of high-energy physics we're only beginning to uncover. And as we'll see next, some gamma-ray signals don't just challenge our understanding of clusters, they seem to defy the very laws of physics themselves. Now let's turn our attention to another head-scratcher, the extragalactic background light paradox. Picture this: the universe is filled with a faint glow of starlight, the combined light from all the stars and galaxies that have ever existed. This is called the extragalactic background light, and it's everywhere like a cosmic fog. When high-energy gamma rays travel across the universe, they should bump into this starlight and get absorbed, especially at the highest energies. It's like shining a flashlight through thick mist. Some of the light gets scattered or blocked. Scientists have calculated exactly how much gamma radiation should be lost along the way, based on how much starlight is out there. But here's the twist: some of these gamma rays arrive at our telescopes completely unharmed, as if they never encountered any starlight at all. This shouldn't happen. It's like throwing a ball through a wall and watching it come out the other side untouched. So what's going on? One possibility is that our measurements of the extragalactic background light are off. Maybe there's less starlight out there than we thought. But that's hard to believe given how carefully astronomers have mapped it. Another, more exciting idea is that these gamma rays are bending the rules of physics. Maybe they're interacting with space-time in ways we don't yet understand, or perhaps they're evidence of exotic particles that don't behave like ordinary light. Some theories even suggest that these gamma rays could be hinting at tiny ripples in the fabric of the universe itself, revealing secrets about quantum gravity. What makes this paradox so fascinating is that it forces us to question not just our understanding of gamma rays, but the very nature of light and the structure of the cosmos. And as we'll see next, some gamma-ray mysteries aren't just about what we detect, they're about what's missing. Now, let's shift our gaze to something equally puzzling: the mysterious gamma-ray halos surrounding certain galaxies. Imagine looking at a galaxy not just as a bright disk of stars, but as a shimmering sphere of faint, high-energy light. These ghostly gamma-ray envelopes stretch far beyond the visible edges of galaxies, like cosmic auras we can't fully explain. What's creating these halos? One leading idea points to dark matter. If dark matter particles collide and annihilate, they could produce gamma rays, painting these faint glows around galaxies like invisible ink suddenly made visible. It's a tantalizing clue in the hunt for dark matter's true nature. But there's another possibility: cosmic rays. These high-energy particles, accelerated by supernova or black holes, might interact with gas and magnetic fields in the outskirts of galaxies, generating gamma rays as they travel. Think of it like cosmic fireworks, particles crashing into each other, lighting up the galactic neighborhood in ways we're just beginning to detect. The tricky part: these halos are incredibly faint, buried in a sea of other gamma-ray signals. Teasing them apart requires painstaking analysis, like listening for a whisper in a thunderstorm. And the more we study them, the stranger they seem. Some halos appear too large or too bright for known cosmic ray processes, while others don't quite match predictions for dark matter either. Could these gamma-ray halos be a mix of both, or are we seeing something entirely new, a hidden mechanism that reshapes how energy moves through galaxies? Either way, these faint glows are forcing us to rethink what happens in the quiet, unseen corners of the universe. And as we'll soon discover, some gamma-ray mysteries aren't just about what surrounds galaxies, they're about what's lurking in the emptiest spaces of all. Now, let's venture into one of the most baffling corners of gamma-ray astronomy, the mystery of ghost gamma rays. Picture this: telescopes detect bursts of high-energy light, but when scientists turn their instruments to look for the source, they find nothing. No galaxies, no black holes, no supernova, just empty space. It's as if the universe is playing a cosmic game of hide and seek, leaving behind gamma-ray fingerprints with no obvious culprit. So what's going on? One possibility is that these ghostly signals come from dark matter. If dark matter particles decay or collide in the void between galaxies, they could produce gamma rays without any visible trace. It's like hearing footsteps in an empty hallway. Something unseen must be there. Another wild idea involves quantum spacetime. Some theories suggest that the fabric of space itself might flicker at tiny scales, creating gamma rays as a byproduct. Imagine the universe's vacuum humming with energy we barely understand. But here's the twist: not all ghost gamma rays behave the same. Some appear in predictable patterns, while others flicker randomly, defying explanation. Could there be multiple hidden processes at work? Or are we seeing the limits of our telescopes, missing faint sources buried in the noise? What makes this mystery so thrilling is its sheer audacity. These gamma rays challenge us to consider that the emptiest parts of space might be hiding secrets, whether invisible matter, exotic physics, or something entirely unexpected. And as we'll see next, even the most persistent gamma-ray puzzles have a way of leading us deeper into the unknown. Now, shifting our gaze to the heart of our galaxy, we encounter another enigma: the mysterious 511 kiloelectronvolt gamma-ray line emanating from the Milky Way center. This isn't just any gamma-ray signal. It's the unmistakable fingerprint of positrons, the antimatter counterparts to electrons, annihilating with ordinary matter. Every second, countless positrons meet their end here, releasing gamma rays at this precise energy. But here's the puzzle: where are all these positrons coming from? For decades, scientists have proposed theories, from exotic astrophysical processes to more speculative ideas. One leading candidate involves radioactive elements forged in supernova or neutron star collisions. When certain unstable isotopes decay, they spit out positrons, which could explain the signal. But there's a hitch: the sheer volume of positrons needed doesn't quite match what we'd expect from these sources alone. It's like finding a river flowing through a desert. You'd expect a hidden spring somewhere, but no one's found it yet. Then there's the dark matter angle. If hypothetical dark matter particles, like weakly interacting massive particles, were to collide and annihilate, they could produce positrons as a byproduct. It's a tantalizing idea, but so far, no direct evidence links this signal to dark matter. And let's not forget more mundane explanations, like X-ray binaries or even outbursts from our galaxy's supermassive black hole, Sagittarius A*. Yet none fully account for the persistent, widespread glow. What makes this mystery so compelling is its longevity. Unlike fleeting gamma-ray bursts, this signal has been steady for over 50 years, defying easy explanation. It's a cosmic whisper that refuses to fade, challenging us to rethink everything from stellar physics to the nature of antimatter itself. And as we'll soon see, the universe has even more gamma-ray surprises in store, each one pushing the boundaries of what we thought possible. Now, let's turn our attention to the echoes of cosmic explosions, gamma-ray signals that linger long after the fireworks of a supernova should have faded. These delayed emissions are like ghostly whispers from the past, challenging our understanding of how particles behave in the aftermath of stellar death. When a massive star explodes as a supernova, it doesn't just vanish. it leaves behind a remnant, a turbulent cloud of debris racing outward at incredible speeds. According to textbook models, this debris should accelerate particles, producing gamma rays that fade as the remnant expands and cools. But here's the twist: some supernova remnants keep emitting gamma rays for far longer than expected, sometimes even thousands of years after the explosion. It's as if the universe hit the snooze button on these cosmic alarms, and scientists are scrambling to figure out why. One possibility is that the interstellar medium, the sparse gas and dust between stars, is playing tricks on us. As the remnant plows through this material, shock waves could continuously re-energize particles, creating fresh gamma rays long after the initial blast. Another idea points to hidden pulsars or neutron stars within the remnants, their powerful magnetic fields acting like natural particle accelerators. Yet even these explanations struggle to account for the sheer persistence and intensity of some of these signals. What makes these gamma-ray echoes so fascinating is what they reveal, or fail to reveal, about the extremes of particle physics. If our models of acceleration and interstellar interactions are missing something, these remnants could be pointing the way to new physics, like exotic particle behavior or unseen energy sources. And as we'll see next, the gamma-ray sky has even more puzzles waiting to unravel, each one a clue to the universe's best-kept secrets. Now, let's push the boundaries of energy even further, into the realm of the unimaginably powerful. Some gamma rays don't just break records, they shatter our expectations entirely. These are the ultra-high energy gamma rays, packing a punch so intense they defy the very laws we thought governed cosmic particle physics. At energies above 1 trillion electron volts, what scientists call the tera-electron volt, or TV range gamma rays, should be incredibly rare. The universe has natural limits on how much energy particles can reach, based on how they're accelerated and how far they travel without losing steam. But here's the shocker: telescopes keep spotting TV gamma rays where they shouldn't exist, in quantities that make no sense. It's like finding a car engine that somehow runs faster than its fuel should allow. So what's behind this cosmic overachievement? One leading theory points to extreme environments, places like the hearts of active galaxies or the wreckage of supernova explosions, where conditions are so violent they might push particles beyond known limits. Imagine a natural particle accelerator, far more powerful than anything we've built on Earth, lurking in the depths of space. But there's a wilder possibility: these gamma rays might be hinting at physics we haven't discovered yet. Some researchers speculate that exotic particles or even cracks in Einstein's theory of relativity could be at play. If that's true, every rogue TV photon could be a clue to rewriting the rulebook of the universe. What makes this mystery so thrilling is its stakes. If these gamma rays are just coming from extreme but ordinary cosmic events, they'll teach us about the universe's most chaotic corners. But if they're signs of new physics, they could redefine reality itself. And as we'll see next, the gamma-ray sky has even stranger surprises in store, each one a whisper from the edge of our understanding. Now, let's turn our attention to a cosmic contradiction that's baffling astronomers. Galaxies that should be silent, suddenly screaming in gamma rays. Picture a library where every book sits untouched for decades, and then, out of nowhere, one shelf bursts into flames. That's what happens when a quiet, unremarkable galaxy, one with no active black hole or star-forming frenzy, suddenly erupts with a gamma-ray flare. These aren't just minor flickers. Some of these flares outshine the entire galaxy's normal output, vanishing as mysteriously as they appeared. The big question: what's triggering them? One leading suspect is a supermassive black hole that's been lurking undetected, suddenly waking up to devour a passing star. When a star gets too close, the black hole's gravity shreds it in a tidal disruption event, a cosmic feeding frenzy that can unleash a brief but blinding gamma-ray burst. But there's another possibility: a rare, hyper-energetic supernova. Most dying stars fade predictably, but a handful might collapse into magnetized neutron stars with magnetic fields so intense they could power these bizarre flares. Imagine a stellar explosion so violent it leaves behind a spinning, magnetic powerhouse, pumping out gamma rays like a lighthouse on overdrive. The real puzzle is why we don't see these flares more often. If hidden black holes or freak supernova are the culprits, our galaxy survey should have caught more of them by now. That gap suggests something even stranger might be at work, perhaps a new class of transient events we've barely begun to understand. What's clear is that these flares are rewriting the rules of galactic behavior. They remind us that even the quietest corners of the universe can hide explosive secrets, and sometimes the most ordinary-looking galaxies are anything but. And as we'll see next, the surprises don't stop there, because when it comes to gamma rays, even the emptiest spaces might not be as empty as they seem. Now, let's peel back another layer of this cosmic puzzle where gamma rays and cosmic rays collide in a mystery that defies expectations. You'd think these two high-energy phenomena would go hand in hand like thunder and lightning. But the universe loves to surprise us. Cosmic rays, those ultra-fast protons and atomic nuclei racing through space, should, in theory, be the perfect parents for gamma rays. When they smash into interstellar gas, they ought to produce gamma rays like clockwork. So why do some regions of the sky glow with gamma rays but lack the expected cosmic rays, while others buzz with cosmic rays but show no gamma ray signature? It's like finding footprints without a walker or a shadow without an object. One explanation points to the journey of cosmic rays themselves. These particles don't travel in straight lines, they zigzag through tangled magnetic fields, which could scatter them far from where they originated. By the time they interact to produce gamma rays, they might be light years away from their birthplace, leaving us with a mismatched map. Then there's the possibility that not all gamma rays come from cosmic rays. Some might be born from dark matter annihilation or exotic astrophysical processes, muddying the waters further. And let's not forget the interstellar medium, the gas and dust between stars, which might absorb or alter cosmic rays in ways we don't yet understand, skewing the relationship. The most tantalizing clue: some gamma rays seem to come from regions where cosmic rays are mysteriously absent altogether. This could mean we're missing a hidden source of gamma rays, or that cosmic rays behave in ways our models can't yet predict. Either way, this cosmic mismatch is a glaring reminder that our understanding of high-energy physics is still full of gaps. And just when you think the plot couldn't thicken further, the next mystery takes us even deeper into the ancient whispers of gamma rays from the dawn of time itself. Now let's journey back in time, way back to when the universe was just a cosmic infant. Imagine the first flickers of light, the birth of stars, and the violent eruptions of black holes, all leaving behind echoes in the form of gamma rays. These aren't just any gamma rays, they're primordial, carrying secrets from the dawn of existence itself. Detecting gamma rays from the early universe is like finding fragments of a billion-year-old letter. Some might come from the first generation of stars, monstrous giants that lived fast, died young, and exploded in spectacular supernova, flooding space with high-energy light. Others could be the last whispers of ancient black holes, devouring matter in the universe's chaotic youth. And then there's the wildest possibility: gamma rays that trace all the way back to the Big Bang, a relic of the moment everything began. But here's the catch: the farther back we look, the fainter these signals become, drowned out by the chatter of more recent cosmic events. It's like trying to hear a whisper in a thunderstorm. Scientists have to sift through the gamma ray background with extreme care, searching for subtle patterns or energy signatures that betray their ancient origins. Some theories suggest these primordial gamma rays might cluster in specific ways or carry unique spectral fingerprints, hints that could reveal whether they're from stars, black holes, or something even more exotic. The most tantalizing idea: If we could isolate gamma rays from the Big Bang itself, they might hold clues about the universe's very first moments, physics so extreme it defies our current understanding. It's a long shot, but even the possibility keeps researchers digging deeper into the data. And just when you think the mysteries can't get more profound, the next one takes us into the shadows where gamma rays defy all known explanations. Now let's turn our attention to something even more puzzling: gamma rays that don't fit the mold. These aren't just mysterious, they're downright strange, with energy signatures that defy everything we know about cosmic objects. Scientists call them dark gamma ray sources, not because they're invisible, but because their origins are shrouded in complete mystery. Picture this: telescopes pick up gamma rays with patterns that don't match any known star, black hole, or galaxy. It's like hearing a song in a language no one speaks familiar enough to recognize as music, but impossible to decipher. Some of these signals might come from exotic particles we've yet to discover, like hypothetical dark matter particles colliding and annihilating in deep space. Others could be the fingerprints of entirely new astrophysical phenomena, something beyond our current textbooks. One leading theory suggests these gamma rays might be tied to quantum foam, a turbulent, microscopic structure of spacetime predicted by some theories of quantum gravity. If true, these faint signals could be our first glimpse into physics at scales so tiny they rewrite the rules of the universe. Another idea points to hidden pulsars or black holes, ones that behave so differently from known ones that they're effectively invisible in other wavelengths. But here's the real kicker: every time researchers think they've pinned down an explanation, another odd gamma ray source pops up, throwing the puzzle back into chaos. It's a reminder that space still holds secrets we haven't even dreamed of yet. And just when you think the cosmos can't get any weirder, the next mystery bends reality itself. Gamma rays that act like they're passing through invisible cosmic lenses. Now, let's take a closer look at one of the most mind-bending mysteries in gamma ray astronomy: cases where these high-energy photons appear to bend or magnify as they travel through space. Scientists call this phenomenon gamma ray lensing, and it's as puzzling as it is rare. Imagine gamma rays acting like light passing through a cosmic magnifying glass. Normally, this distortion happens when massive objects like galaxies or black holes warp spacetime, bending the path of light behind them. That's gravitational lensing, a well-known effect predicted by Einstein. But here's the twist: some gamma rays show lensing-like behavior where there's no obvious massive object to cause it. It's like seeing a shadow with nothing casting it. One possibility is that invisible clumps of dark matter are doing the bending. These elusive particles could create dense, unseen regions of gravity strong enough to deflect gamma rays without emitting any light of their own. Another theory suggests turbulent magnetic fields in interstellar space might be twisting the paths of these high-energy photons in ways we don't yet understand. Then there's the real head-scratcher: a handful of gamma-ray bursts appear magnified, as if something amplified their signal on the way to Earth. Could this be a sign of exotic physics, like hidden dimensions or quantum gravity effects playing tricks on light? Or are we just seeing the fingerprints of cosmic structures too faint for our telescopes to spot? Every unexplained lensing event forces scientists to rethink what they know about gravity, dark matter, and even the fabric of spacetime itself. And as we peel back the layers of this mystery, we're left with an even bigger question: what else is out there, bending the rules of the universe? Up next, we'll explore how our own galaxy is wrapped in a mysterious gamma-ray fog, one that might hold clues to its most violent past. Now, shifting our gaze closer to home, we encounter another cosmic puzzle: the Milky Way's eerie gamma-ray haze. Picture our galaxy wrapped in a faint, glowing fog of high-energy light, stretching far above and below the galactic plane. This isn't the work of ordinary starlight or even the usual suspects like pulsars or supernova remnants. Instead, it's a diffuse, enigmatic glow that has astronomers debating its origins. One leading theory points to cosmic rays' high-speed particles slamming into interstellar gas, producing gamma rays as a byproduct. But here's the catch. The haze distribution and energy don't quite match what we'd expect from this process alone. It's like finding footprints that don't match the shoes of the suspect. Then there's the dark matter angle. Some researchers suggest this haze could be the long-sought signal of dark matter particles annihilating in the Milky Way's heart, releasing gamma rays in the process. It's a tantalizing idea, but so far the evidence remains inconclusive. The haze's smooth, widespread nature doesn't perfectly align with predictions for dark matter, leaving room for doubt. Another possibility, a violent chapter in our galaxy's past. Imagine a colossal outburst from the supermassive black hole at the Milky Way's center, spewing energy and particles into the surrounding space. Such an event, occurring millions of years ago, could have left behind this lingering gamma-ray fog as a fossil of that ancient turmoil. What makes this mystery so compelling is that each explanation, cosmic rays, dark matter, or a galactic eruption, comes with its own set of unanswered questions. The haze is a reminder that even our home galaxy holds secrets we've yet to unravel. And as telescopes grow more sensitive, we might finally pinpoint what's casting this ghostly glow across the Milky Way. Up next, we'll turn our attention to the faint whispers of gamma rays coming from tiny dwarf galaxies, clues that might just crack the dark matter code. Now, let's zoom in on some of the universe's smallest galaxies, dwarf galaxies, where faint whispers of gamma rays might be hiding one of cosmology's biggest breakthroughs. These tiny, dim galaxies are cosmic underdogs, often overlooked, but they could hold the key to solving the dark matter mystery. Here's why they're so intriguing. Unlike large galaxies like the Milky Way, dwarf galaxies have very few stars and almost no gas, meaning there's little conventional activity to produce gamma rays. Yet, some of them emit a faint but persistent glow in this high-energy light. If not from stars or cosmic rays, where is it coming from? Many scientists believe this signal could be the long-awaited fingerprint of dark matter. The reasoning is simple. Dwarf galaxies are packed with dark matter far more than normal matter. If dark matter particles collide and annihilate, as some theories predict, they should release gamma rays, exactly the kind of faint, steady emission we're detecting. It's like hearing a whisper in a quiet room. The signal is subtle, but it stands out because there's so little background noise, but not everyone is convinced. Skeptics point out that the gamma-ray signals are still too weak to declare victory, and alternative explanations exist. For instance, a population of hidden pulsars too dim to spot individually could be responsible. Or perhaps cosmic rays, even in these sparse galaxies, are interacting in ways we don't yet understand. What makes this mystery so exciting is the stakes. If these gamma-ray whispers truly are from dark matter, it would be one of the most significant discoveries in modern physics, finally revealing the nature of this invisible cosmic glue. But if not, it forces us to rethink how these tiny galaxies produce such unexpected signals. Either way, dwarf galaxies are proving that even the faintest voices in the cosmos can have the loudest implications. Up next, we'll explore how the gamma-ray sky isn't as steady as we once thought. Some parts flicker unpredictably, hinting at dynamic processes we're only beginning to grasp. Now, let's shift our gaze to something even more puzzling. The gamma-ray sky isn't as calm and steady as we once believed. Parts of it flicker and change brightness unpredictably, like a cosmic light show with no clear schedule. This erratic behavior, known as the time variable background, throws a wrench into our understanding of how gamma rays are produced across the universe. At first glance, you'd expect the gamma-ray background to be smooth and unchanging, a steady hum of high-energy light from countless distant sources. But telescopes like Fermi have spotted patches of the sky where the gamma-ray signal fluctuates, sometimes brightening, sometimes fading over weeks, months, or even years. The big question is, why? One possibility is that we're seeing the aftereffects of violent, short-lived events like gamma-ray bursts or flares from supermassive black holes. These cataclysms could leave behind echoes that ripple through the gamma-ray background, creating temporary hotspots. Another idea is that swarms of pulsars or microquasars, objects that flicker on their own, might be clustering in ways we can't yet detect individually, creating a collective flicker effect. But here's the twist: some of these variations don't match any known astrophysical sources. That has led to wilder theories like exotic dark matter interactions or even quantum foam, a hypothetical frothy structure of spacetime itself disrupting gamma rays on their way to us. It's as if the universe is teasing us with clues we can't quite decipher. What makes this mystery so frustrating and thrilling is that our current telescopes lack the precision to pinpoint what's causing these fluctuations. Future observatories with sharper vision and better time resolution might finally crack the code. Until then, the flickering gamma-ray sky remains a tantalizing puzzle, reminding us that even the most subtle changes can reveal the universe's deepest secrets. Coming up, we'll venture into even more speculative territory where gamma-ray anomalies might hint at something far stranger, a breakdown in Einstein's theory of relativity itself. Now, let's take a step into the realm of the truly mind-bending, where gamma rays might be whispering secrets about the very fabric of reality itself. Some of the strangest anomalies in the gamma-ray background could be hinting at something even more profound than dark matter or black holes, flaws in Einstein's theory of relativity or the granular structure of spacetime. Imagine spacetime not as a smooth, invisible stage where cosmic events play out, but as a frothy, turbulent sea at the smallest scales. This idea, known as quantum gravity, suggests that spacetime itself might have a grainy texture when you zoom in far enough, like pixels on a screen but unimaginably tiny. If that's true, ultra-high-energy gamma rays traveling across the universe might stumble over this grainy structure, leaving subtle distortions in their signals. Here's where it gets wild. Some gamma-ray bursts and distant blazars appear to arrive at Earth with tiny delays, high-energy photons showing up slightly later than their lower-energy counterparts. According to Einstein, all light, no matter its energy, should move at the same speed in a vacuum. But if these delays are real and not just measurement errors, they could be the first hints that relativity breaks down at extreme energies, revealing the quantum nature of gravity. Of course, not everyone's convinced. Skeptics argue that these delays could come from more mundane sources, like interactions with interstellar dust or magnetic fields. But if future telescopes rule those out, we might be staring at evidence of a theory that unifies gravity with quantum mechanics, a holy grail of physics. The implications are staggering. Gamma rays, often seen as mere byproducts of cosmic violence, could become our best tool for probing the universe's most fundamental rules. Whether these anomalies hold up or not, they remind us that the cosmos still has surprises lurking in the most unexpected places, even in the flicker of a single photon. Up next, we'll tackle the final mystery, one that makes us question whether the gamma-ray background is even real in the way we think it is. But here's the twist: what if the gamma-ray background isn't a background at all? As we wrap up our journey through these cosmic puzzles, we arrive at a question that turns everything on its head. For decades, scientists assumed the faint glow of gamma rays filling the universe was smooth and uniform like a cosmic fog. But what if it's just an illusion, a trick of perspective? Think of it like standing in a forest at night. From a distance, the trees blend into a dark, shapeless mass. But as you get closer, you start to see individual trunks, branches, and leaves. The gamma-ray sky might be the same way. What we call the background could actually be the combined light of millions of distant sources, pulsars, black holes, or even entirely new cosmic objects too faint for our telescopes to pick out individually. This idea isn't just speculation. Some studies suggest that as our instruments improve, more of the so-called background resolves into distinct points. The Fermi Gamma Ray Space Telescope, for example, has already turned some diffuse patches into catalogued sources. If this trend continues, we might eventually erase the gamma ray background entirely, replacing it with a sky full of identifiable objects. But there's a catch. Even as telescopes get sharper, a portion of the gamma ray glow stubbornly refuses to resolve. Is this the real background, or are we just hitting the limits of our technology? The answer could redefine how we map the universe's most energetic light. So here we are at the end of our 25 mysteries, left with a humbling thought. Sometimes the universe's greatest secrets aren't hidden in the exotic or the extreme, but in the very way we perceive the cosmos. What we call a background might just be a placeholder for discoveries yet to come. And with that, we've reached the end of our cosmic detective story, but the search for answers is far from over. If these mysteries sparked your curiosity, don't forget to subscribe and hit the bell so you won't miss our next deep dive into the universe's unsolved puzzles. Drop a comment below telling us which gamma ray mystery blew your mind the most. Until next time, keep looking up. From the enigma of dark matter's hidden signals to the whispers of ancient gamma ray bursts, these 25 mysteries aren't just cosmic curiosities, they're portals to understanding the universe itself. Each unanswered question, from the Fermi Bubbles' eerie glow to the Milky Way's unexplained gamma ray haze, reveals how much we still have to learn about the forces shaping reality. Whether it's the puzzle of antimatter swirling at our galaxy's core or the possibility that gamma rays might expose quantum gravity's secrets, one thing is clear: the cosmos loves keeping us on our toes. But here's the beautiful part: every mystery we've explored today isn't a dead end. It's an invitation to dig deeper, to question assumptions, and to marvel at how much wonder lies just beyond the edge of our current knowledge. And with telescopes growing sharper and scientists tackling these riddles from bold new angles, the next groundbreaking discovery could be just around the corner. That's where you come in. The universe's secrets aren't just for researchers in lab coats, they are for anyone who dares to look up and wonder. So if these gamma ray mysteries left you as awestruck as they left us, hit that subscribe button and ring the bell. You won't want to miss the moment we crack one of these cosmic cases wide open. Drop a comment below telling us which mystery hooked you the most. Was it the ghostly gamma rays from nowhere, or the way pulsars defy the rules? Let's keep the conversation as vibrant as the universe itself. Until next time, stay curious, stay amazed, and remember, the greatest discoveries often start with a simple question.